Perfect. So yeah, today I'm going to be continuing the overview of action policies in Monty. And yeah, I think although we'll kind of record this so that we can, share it in the future, the emphasis is definitely on the discussion part. So please definitely stop me and either ask questions or raise objections or whatever it may be.
No problem. That's par for the course.
So yeah, so continuing on from last time, I'm just going to talk briefly about a few kind of points here around. I thought it'd be useful to just talk a bit about the kind of core anatomy, and then kind of a bit of the philosophy of learned versus hardwired policies. Then finish up the kind of discussion of model-free policies with some discussion of abstract spaces, and then get into the model-based policies, and then finally kind of hierarchical policies and kind of future directions. So yeah, we talked a bit about last time how kind of model-free policies generally map onto subcortical structures in the brain, whereas the model-based ones map onto cortical structures. So I just thought it was worth kind of pulling up a figure so people can see the kind of basal ganglia, where they are in the brain, as these are generally the kind of regions that are most associated with model-free learning. They have a significant involvement in kind of motor or like action initiation and control. And there's these kind of significant dopamine projections for the substantia nigra, which are implicated in reinforcement learning type learning. Whereas for model-based,
on the just by the way, on the previous slide, you didn't highlight the cerebellum, which is
Sure.
the bottom right there, and that's very heavily associated with learning in movement, but sort of apparently mostly small movement changes and timing changes, and but it's a huge part of the non-model free learning system, although it seems to be doing fine-tuning of lots of things.
Right.
Just want to point that out, because if you're cerebellum person listening, they say, wait a second, you're talking about, you didn't mention the cerebellum. It's got more cells than the neocortex.
And then you have, like the brainstem down here, which is like where the actual motor signals go out and affect the muscles in the body.
Right, and including
and then the thalamus is kind of involved in everything.
Right, and the spinal cord does reflex reaction, so there's a lot of, pretty much the entire body is a model-free learning system,
Yeah, and then basal ganglia get projections from the cortex, and then my understanding is the recurrent loop is then kind of backed by the thalamus. And then model-based is kind of the model we're kind of going for is where essentially you have these object models learned in each cortical column. And you can kind of think of these as represented across the fourth and the sixth layers of each cortical column. That's kind of where the model generally resides, but of course there's many different elements to a model. And it seems L5 is probably the most kind of important region in terms of kind of action planning for each column, because this is where you get a direct motor projection. And this is two subcortical structures. So both a connection that goes to the thalamus and then one that goes to brainstem nuclei generally. But what's interesting is that this occurs in every column in the brain, essentially, regardless of whether it's prefrontal cortex or kind of ostensibly sensory cortex or motor cortex. This is kind of a very prominent projection. And this is quite unusual in terms of how motor outputs are often formulated, that you have this kind of direct projection from all levels of the system.
Yeah, it's worth pointing out that is really the only direct output from the cortex. This is right. It's motor. So when we think about this, a sensory motor system, the only output is motor. I mean, there's some, obviously there's a bunch of other sort of, modulator connections, things like that. But this is viewed as the output from the cortex. So.
Right.
Yeah.
Yeah, and then last time I guess we were talking about kind of separation of model-free and model-based, and I mean, maybe it's obvious, but I guess what I was just trying to get at with like the example of like riding a bike or whatever is that I guess like if you were trying to teach your child to ride a bike, that initial stage of them like getting onto the bike and being kind of told, oh, you need to pedal, or maybe them seeing an adult pedaling and just having some basic idea of what to do is probably more of kind of a model-based thing. But then, yeah, the kind of fine motor coordination that's required to actually balance a bike and that kind of innate knowledge that comes over time is more of a kind of model-free type. So I guess a lot of actions end up involving both kind of types of policies. So yeah, so that's just kind of revisiting the model free versus model based with a kind of focus on the anatomy. Another thing that I think is just worth kind of touching on in terms of the sort of philosophy of policies and how we're kind of approaching them in Monty is like a lot of what I've described that we've implemented might come across as kind of like hardwired policies where we're trying to almost like cover the entire space of any policy the system might need and kind of build that from the ground up, which would be kind of reminiscent of good old-fashioned AI. But that's definitely not the intent. The intent is to kind of design a few key policies that we kind of believe are important, and then these can be kind of almost seen as primitives that more complex policies can build off of, so that not everything is kind of totally from scratch or totally kind of needs to be learned through some sort of random exploration, but that the kind of system has these starting points that it can leverage. And so, yeah, we kind of touched on this briefly last time, but that could, for example, include kind of state switching of the kind of model-free policies that's controlled in some, top-down manner with a more model-based policy, as well as kind of parameter adjustment. So yeah, with the state switching, you could be like, okay, start following the minimal curvature, now switch to the maximum curvature, or with kind of parameter adjustment, you can imagine kind of that sort of momentum in terms of how much you either persist in moving in the same direction or move kind of randomly. If you're just kind of trying to sense an area over and over again because it's kind of a noisy input and you really want to kind of clarify the nature of that information, that's a very kind of simple adjustment that could be made. But if you're just kind of trying to quickly get as much information as possible over a broader area, then it's natural you might kind of do more of a sort of high momentum movement.
It's interesting to think about, I mean, hardwired versus learned, and we have model versus model free. A lot of the model free learning, I mean, it's learning, right? There's stuff that goes on, like riding the bike. It's a model free learning. So some of the cortex has to deal with, it has to deal with a body that's changing. It has to deal with a set of model free action policies that are changing over time. And our bodies grow, right? We get longer limbs, we have injuries, whatever. And the cortex, I just want to point out that the cortex doesn't deal with just with hardwired policies. It deals with other learning policies that might be model free, but they're still learning. And so it's worth bearing in mind that the cortex has to deal with this. The world it's interacting with, the other parts of the brain it's interacting are not static. So there might be some really hardwired things like reflex reactions, but most of what's going on subcortically are also changing over time. And the whole system has to settle on that. The whole system has to constantly adjust. It's just something to keep in mind as we think about this.
Yeah, right. Yeah, no, it's an interesting point.
But from Monty, we can have some hardwired stuff that don't learn, but just remind people of that.
Yeah.
Reminding myself.
Okay, nice. So, and then in terms of kind of finishing up the model free policy discussion, I just thought it'd be interesting touching on abstract spaces, which we didn't get around to last time. So I think in general, it's fair to kind of say abstract spaces are really just defined by kind of abstract actions. It's not like there's anything that special about the space. Something like a family tree or kind of simple multiplication kind of fits naturally into some space, some subset of 3D space. But what really kind of defines it as abstract is the movements that you are kind of doing through that space. So in a family tree, there's these discrete relations like parent and grandparent and grandchild. which kind of move you around this space in very defined ways, and similarly with kind of mathematical operations. And last time I talked about these kind of model-free policies that we've implemented for example, following principal curvature on object surfaces. And so it's just interesting to, I mean, this is speculative, it's not anything we've implemented, but it's just kind of interesting to think, I guess, about what sort of analogies there might be in more abstract spaces. And I think it's, useful if you kind of imagine that generally information is kind of clustered.
I'm confused, Niels. Are we talking about
Yeah.
abstract spaces in the model-free action
Yeah.
policies?
Yeah.
How that seems odd to me.
Yeah.
I would have assumed that abstract spaces would always be model-based. I mean, by very definition, they're not real-world things that we could have evolved with.
Yeah.
So why would you consider them part of the model-free space here?
I guess just thinking of it as kind of simple heuristics of how to kind of move through space that could apply just as much in abstract spaces as they do in.
I guess I'm challenging that. It seems to me that the abstract spaces would be almost the definition of something that has to be model-based.
Yeah.
I mean, do you disagree with that? I mean, it's like my spinal cord can't know about family trees, or
no, I
mathematics.
And I agree with that.
It just seems like
I guess I can imagine that there would be ways, I guess, for the kind of cortical structures, if it's useful to kind of learn simple heuristics about how to process more abstract inputs. And
yeah, but I can imagine in terms of the model-free subcortical stuff, it's very physical, right? I mean, you got your finger touching something, or you're trying to balance, or you're walking, or you're you reflex reactions to physical things in the world. But when it comes to like abstract spaces, I can't imagine what a subcortical relationship could be. It's like there's nothing physical about it, right? It's all in the model. It's all in something I've learned about the world that isn't physically, manifested in them. Like the parent-child relationship is not like something I can detect physically. It's something I have to know or learn about. So I'm not sure.
I guess I'm just thinking if action in abstract spaces is more kind of like essentially how you move your attention through that space.
But wouldn't that be cortical? I mean, how could that be subcortical? I guess I just don't get that.
I guess it comes back to whether there could be some sort of more model-free type stuff as well in cortical circuits.
Okay, all right. So that would be the.
So I'm not arguing that this would happen in subcortical structures.
Okay.
But I guess what I'm just arguing is that, like, generally the simpler of the two, of model-free and model-based, is model-free. So if the cortex is capable of model-based, then maybe it uses some kind of more model-free heuristics.
Well, that's an interesting question. Right. That's an interesting question. Are there model-free action policies in the cortex itself? And I've never thought about that question. My initial assumption would say no, but I haven't thought about it. And because whatever it is, it has to work across all modalities, across everything, right? It has to be, up to now, everything in the cortex, everything in a learning module, a cortical column, has to be generic enough to work for everything, every kind of thing you might do, physical things and abstract things. And now we're saying, is there an action-free policy that similarly works? And it's an interesting question. I don't really, now I know where you're coming. It could be in the cortex itself, but it'd have to be something that applies everywhere. So maybe that's what you're talking about.
Yeah, and so this is very speculative. So maybe this is totally wrong. But I guess what I was just thinking was that there seems to be maybe some kind of symmetry between what we kind of intuitively seem to do when we're exploring, an object with our finger, and what we might mentally be doing when we would explore a more kind of abstract space. So if you kind of imagine that the kind of dimensions of information is often kind of is clustered in kind of high density regions, which might be kind of, if they're Gaussian in each dimension, it's has kind of ellipsoid type structure. Then you can kind of think like following the minimum and maximum curvature on this manifold is essentially following the kind of local principal components, like the dimensions of most variation. And so to kind of make that a bit more concrete, like, if you are kind of thinking about someone's political views in general, that might fall into this kind of two-dimensional space of kind of authoritarian versus libertarian and left-leaning versus right-leaning. And again, this could be wrong, but if there's some sort of analogy to kind of how your kind of finger notices kind of the curvature of a cylinder and then kind of finds those two directions the most interesting, both the kind of maximal curvature and the orthogonal direction. Maybe there's kind of something similar in these kinds of abstract spaces where you would kind of explore primarily along these dimensions when trying to kind of understand someone's political views.
If
but
I
maybe
was,
it's a stretch.
It's a bit of a stretch. If I were to pursue this further, I would say, well, if I'm going to come up with some model-free action policies in the cortex, I'd want to see that the same policies apply to vision, touch, and hearing. Not just like, political persuasion. It's like, if it's going to be in the cortex, it's got to apply to everything. So, what would be equivalent to vision? Or what would be equivalent to audition? It's not, you couldn't consider the abstract spaces, but it's got to apply to other things too, which are, universal. So it's just something to think about.
Yeah. Yeah. I guess that's what I was trying to get at with this analogy of kind of the surface of kind of manifolds in abstract space and the kind of surface of objects, or you can also think of like in vision, you sort of have these principal axes of the object, which seem to be kind of like the dominant sort of directions and the kind of the points of symmetry around which kind of the object tends to be reflected, and that's often kind of how we just tend to understand objects. So yeah, maybe there's some similarities there. And then, if you're kind of studying a metro line, which is a graph, in general, your eyes are going to either follow kind of minimal variation in perceptual space, which is, just the line color. So, okay, that might be just subcortical, but then, or kind of more abstract space, you kind of are following some line name. But yeah, I can also see how that could be put down to more of a model-based policy. So maybe it's not that relevant.
Well, it's also, in our work, of course, we've got to get the basics of Monty first has to solve, all the sort of physical world interactions. So it's fun to think about. It's fun to think about abstract spaces, but it's not our first thing to go after.
Right. Yeah, that should be, if anyone's kind of watching this video somewhere, please watch the first one first, which gives broader context. As Jeff points out, the abstract space is definitely the more just kind of niche stuff that we're thinking about for the long term, not the current work. But yeah, maybe that's a good way to segue to model-based policies, unless anyone had any other comments or questions. Cool. So as we kind of touched on last time, the model-based policies are going to leverage learned models of objects in order to make more kind of planned, deliberate action proposals. And we really have two that are kind of currently implemented in Monty. And again, this is kind of a situation where we're sort of crafting these policies, but they can be kind of used as primitives for more kind of general policies and kind of represent.
Are both of these basically all around learning and inference? I mean,
yeah.
Right. I mean, if I think about, we're talking about action policies in the cortex, I'm thinking like, how does the cortex achieve some results in the world, the movement? But we're not talking about that here, right? We're just talking about like, how's the cortex learn objects and how does it infer them? Is that correct? Yeah. All right.
No, that's correct. That's a good point. Yeah, not yet changing the state of the world.
Right.
So yeah, and the key one of these is this hypothesis testing policy, which is what I'm going to focus on. And really, this is about how we can efficiently move to features that disambiguate object and identity and or pose. And so the kind of concept, if you imagine, we have multiple models in our memory, like the fork, the spoon, and the knife, and we have some observed object. We're kind of feeling along the handle of this knife. We, at that point, don't know what object it's going to be, but we like a policy that would enable us to kind of efficiently move to this part of the object that's going to very quickly disambiguate between the three of these.
Okay.
So imagine, yeah, the way we're going to do this is what you can kind of call local graph mismatch. And I'll talk later about how kind of hierarchy can fit into this. But essentially, we're going to take the most likely object hypotheses we have and use the most likely poses we have associated with those and look for kind of mismatch in these kind of aligned graph regions. So breaking down that a little bit more, imagine our two most likely objects are a spoon and a hammer. The true object we're observing is the spoon, and these are the kind of graphs. And right now, our kind of object models are quite simple because we don't have any hierarchy. So we have lots of points, and all these points are associated with this kind of morphological feature of a point normal with some principal curvature directions. And we're going to have some most likely poses associated with these. And what we're going to do is transform essentially internally in like the sort of mental space of the learning module, both of our most likely, these two most likely hypotheses by their most likely poses. And that will give us some alignment just naturally based on kind of how Monty works and how it kind of naturally aligns objects based on its hypotheses. And when you have these two graphs aligned like this, the algorithm in its kind of current version will basically just find the nearest neighbor pair across the graphs. And it then takes the Euclidean distance between those and finds the kind of maximizer. So it's basically going to be the nearest neighbor that is most distant across these graphs. So you can see like,
I don't think that means, how's the nearest neighbor most distant?
Yeah, so basically if you take, so every point in the red graph is going to have a nearest neighbor in the blue graph. So this one will be that, this one will be that. And this point also has a nearest neighbor. It's all the way over here. So this,
but the other,
all the nearest neighbors.
So he's got those three nearest neighbors there, the three dots on the tip of the spoon.
No, but we're only comparing to blue. Because we're comparing across the graph. So we take
right. So you got the blue. What's the closest to the blue dot at the top of the hammer? Is that what you're saying?
Yeah, but I'm going through all the red points, and for each red point, finding the nearest neighbor in the blue graph. So yeah, so this dot's nearest neighbor is this one, this dot's nearest neighbor is this one, and this dot's nearest neighbor is this one. But if we take the distances to their nearest neighbors,
right,
this dot's nearest neighbor, this dot has the largest distance to its nearest neighbor. So that's what the most distant nearest neighbor is. And that the maximizer, that point, is basically the point we want to test. And I'll talk later how this can also apply in abstract spaces or like feature spaces, which would be a more natural comparison.
What is the sort of the everyday logic behind this? I mean, like, why did you pick this? I'm not doubting it.
Yeah, I mean, the reason I picked this is essentially it's this idea that, okay, these two things are aligned, but how are they most different? And they're most different where they don't align. And that's basically what this is looking at. But a more natural way to measure this and test this is, I'll talk about later, if you have hierarchy, and let's say you have a representation of a spoon head, and you have a representation of a handle, and then for the hammer, you also have a representation of a handle, and you have a representation of a hammerhead. You're going to do the same thing, but if you compare them in feature space, the handles are going to be very close together in feature space, but the hammerhead and the spoon head are going to be very far apart in feature space. So that's where you're going to go to. So rather than it being Euclidean distance in physical space.
So you're looking for the biggest maximal difference between these two models at some point, and yet so in the physical non-hierarchical model, it's linear Euclidean distance, but in object models, it's It doesn't have to be physical distance at all.
Exactly.
And
Exactly.
but in the abstract case, how would I define them being different? Just different features then?
Well, so for example, SDR difference. So like
Mm,
the SDR representing the hammerhead and the spoon would be more
mm.
different than
So
the SDR for two different handles.
you're baking this the assumption that the SDRs have or conveying
Well,
uh
we have
yeah,
some way of representing feature alignment, whether that's with SDRs or something else. But yeah, I'm
yeah,
assuming that features aren't just random points in high dimensional space.
yeah. Okay.
Can I
Um,
ask a quick question? This might be obvious, but so this works when we have the when we have already learned the spoon and the hammer, and those points are in memory for Monty, right? In the
right.
unsupervised or in the like from scratch case, um, let's say we like explore the handle and we only have a knowledge of the hammer, but the actual
Mm,
object is spoon. In that case, we don't have like the whole graph of the spoon. And maybe this doesn't apply to the unsupervised case, but like how would you think it
yeah.
would work in that case?
Yeah, no, it's an interesting question. Yeah, so yeah, I should have clarified maybe this is only for inference once we've learned many objects.
Oh,
Um,
right, right.
you can imagine maybe doing something similar at learning where it's like I think I'm like I only know about the hammer, so I think I'm on the hammer, but let me move to what's the most interesting part of the hammer, the hammerhead, because of other objects I do know about. But let's say I don't know about a spoon, and you might more quickly, like just with the way objects are structured, I think there's going to be similarities in terms of like where the most interesting parts are and things like that. But yeah, in general, this isn't set up for kind of use during learning.
Well, for the
Okay.
learning part, you really can't use the nearest neighbor concept. I mean, all you can do is say, hey, if all I know is a hammer, I think I'm touching a hammer, and then all of a sudden I feel something which doesn't fit the model.
Yeah.
Like I didn't,
Yeah,
and then the
it's
question
only
is,
I guess if you already knew some objects, maybe that
right,
could like be used to
but
bootstrap how quickly you learn or something. But yeah,
well, I
Got
think
it.
that learning is going to be, we have to explain both these at the same time in some sense, the learning and the inference. So in general, you're going to, for whatever reason, you're going to send something which doesn't fit the model you have, and then it becomes an interesting question: is how do you decide it's something new, or an extension of the existing model? Those are interesting questions.
yeah,
I
um,
think
yeah, no worries. Yeah, and I guess maybe to answer your question from earlier, Jeff. So if your most likely hypothesis was the hammer, and your second most likely was the spoon, then the algorithm would start with the hammer, and for every point, it would look for the nearest neighbor in the spoon graph, and then in that case, it might be this point, which the most distant nearest neighbor in the spoon graph is this one. So there's some kind of asymmetry depending on which object you are kind of starting with as your base object.
Hmm. The idea of,
Um,
look, if you're searching through objects for nearest neighbors, certainly would work. It seems hard to understand how the neurons would do that. They can't search through lists, you know what I'm saying?
right.
Um, and I don't think I have the answer to this question, but the whole, one of the things, the reason we really love the union property of SDRs is because it allows you to do that without sorting through lists. It's like it somehow allows you
Yeah.
to deal with the ambiguity without saying, okay, let's try all of our hypotheses.
Yeah.
I don't know what's the right thing to do for Monty, but clearly neurons can't do that, if I'm understanding
Right.
what you're saying correctly.
Yeah.
Um,
Mm, at least, yeah, the way we've implemented it. Um,
yeah, okay, just
yeah.
worth pointing
No, I
out.
agree with that. Yeah. Um, Yeah, and so in practice, what this kind of looks like is so you can imagine. So this is the spoon as it's kind of oriented in the real world. This is the agent, the finger, which is touching it here. It's kind of done in a few steps. It's on the fifth step, so it has some sense about what object it's on. And in particular, it thinks it might be the knife or the spoon. And then it's going to. This is in green. These points is in now. It's in its mental space. It's going to align these based on the most likely poses of these two objects. And that gives us kind of what we were expecting, which is that the spoon and the knife are both here, the heads. And then it's going to use that kind of most distant nearest neighbor, and that gives this red point here, just kind of like on the back of the spoon, as the kind of place it should test. And then the policy then the kind of lower level parts of the motor system essentially receive that as a target location, and then the agent moves there. And in the kind of current implementation, it moves there instantaneously. It's kind of teleported to that location, and then it can then keep moving around from there.
You know, it seems like what we have here is sort of a hybrid, which might happen between a single column and multiple columns. A single column, I'm just thinking neurons here. I'm not thinking Monty.
Yeah.
Okay. So in a single column, let's assume it can't check multiple hypotheses. You know, it can't go through a series of objects and saying what's my nearest neighbor to these other objects. All it can do is move along and until your fingertip can move along until it discovers something that doesn't fit the current model. And then says, hey, something's wrong. But interesting, if I have multiple columns active at the same time, and assume that they know where their relative positions are relative to each other, and I say, oh, I think I'm on the spoon. And so now all the columns say, now all the columns, even the ones that aren't receiving input, are saying, okay, we're observing a spoon here. And that column may say, well, in my current location, I'm not on the spoon, right? Or maybe I am on the spoon. So the point is, another column could be observing a distant point of the spoon or the hammer. And if it says, okay, we're all thinking this is a spoon, and I say, well, I know where I am. I shouldn't be observing something because I'm not on the spoon, given our consensus, and yet I am on something. It's like something beyond where the spoon is supposed to be. I'm detecting something. Then I have my ability to, as a column, would say, hey, we ought to go over here because it doesn't fit right. I'm saying, I shouldn't be seeing the spoon. I shouldn't be seeing something here, and I'm seeing something. So let's go look over here. So this kind of, in some sense, I'm trying to imagine how neurons would do this. What you're proposing here, they would do it probably closer to what multiple columns would be doing. They would be sort of doing this. Instead of saying a nearest neighbor, it would be like sort of testing different points on the object simultaneously, including ones that shouldn't have anything. And then someone says, well, you know what, this isn't right. Given that we're supposed to be seeing a spoon, I'm seeing something else. And then visually, our attention would naturally be drawn to that, or tactily too. If I'm grabbing an object with my hand and multiple patches of my skin are touching it, and one of my patches of my skin doesn't fit right, it's just like that isn't what's supposed to feel. Your attention is immediately drawn to that part. And that sort of achieves what you're doing here, I think. So it would be
although I guess in the kind of single finger setting, we would also generally be able to do this, like work out where to test.
But you would, I think you wouldn't test anything until you ran into a problem. Like if I think I'm on the spoon, I'm like, yeah, I'm on the spoon. I move my finger along. I don't say, hey, I'm not proving I don't know. You might just say, I think this is a spoon, until you find out it's not the spoon, or as opposed to saying, hey, I don't know what I'm on. It could be the spoon or the knife or the fork. It might be that. I don't know. I have to think about it. It's an interesting question.
Yeah, but I think it's interesting about the multi-LM, because I guess even if you had one finger, you'd probably still have multiple columns active. And if they kind of inhibited, if there was some kind of mutual inhibition, so that some of them were like, okay, I'm going to have this hypothesis, the other one's going to represent this other hypothesis. And so they're both kind of similar points in space.
I don't think that would be the case. If you have a single hypothesis, that would be voting across the columns. And so everyone would say, hey, you know what? We all think, I mean, the voting, the way we've implemented, the way I think it works, it's kind of it very quickly settles on a answer. It doesn't like, it doesn't, it very quickly settles on the answer. It wants to come to a hypothesis. And as soon as it does, then the different columns could say, this isn't right. I don't have to think about it. I don't know. All right. I'm thinking out loud. Sorry about that. But I guess maybe the general thing to think about here is to keep in mind that what does one column do versus what does multiple columns do in the same region versus what's going to go on in a hierarchy. And those are our two base, those are our three basic scenarios we have to understand: single column, multiple columns working together, and then columns in a hierarchy.
Right.
And so some of these action policies that you're describing here might be mix and match of those different scenarios.
Right.
I'm not objecting to it. I'm just thinking out loud. That's just
Yeah.
all.
Yeah. Right. So yeah, just showing some kind of other examples of this. So, if you have a mug versus a handleless cup, this process might propose that you test the handle here. Here, the knife is the most likely hypothesis. And so to distinguish it from the second most likely, in this case, the fork proposes this location. And I think, yeah, I kind of alluded to this earlier, but I think one nice kind of element of Monty is just its kind of rotation equivariance, where it always accounts in its hypothesis space for the rotation of the object, and the rotation it was kind of learned in the real world, the kind of like initially the sort of like base rotation is it's totally arbitrary. So here you can see if you kind of plot the rotation of the internal models of the knife and the spoon, oriented kind of as they were in the real world, then they don't align. But when the system is sensing it, it can sense the orientation of the handle, and so it just naturally aligns these in its hypothesis space. And then you can see just kind of how over the course of inference, the kind of hypotheses, eventually you might come to the point where you are convinced it's the mug, or you've eliminated all objects but one, but you might still have some uncertainty about the pose, and you can also use this process to infer that. So, oh, I deleted the slide there. A better example is here. So early on in inference, you've sensed the handle, but it can be ambiguous whether the spoon is oriented that way or it's kind of mirror reverse. And so you might test a point like this, but then later on, you might just have some very subtle uncertainty about the pose of the object, like, is it 10 or 20 degrees in particular rotation? And then so bringing everything together, this is showing the model-free kind of curvature, but following policy with the model-based hypothesis testing. And so what you see here is first in white, the the surface agent is following the minimal curvature of the handle. So it's kind of moving to the end. And when it gets to the end, it has a high kind of certainty that it's looking at something like the spoon or the fork or the knife. And then it performs a hypothesis based jump to the head of the object.
When it does
a
a hypothesis based jump, it has one hypothesis in mind. It says, "Oh, is this a fork? Let me test that." Is that what?
Yeah,
it's not like it's not doing fork and knife at the same time, right? It's saying, "Okay,
no, exactly. It's saying this is my most. So here it's like its most likely hypothesis is the knife. It's saying, okay, what else could it be? It could be the spoon, but I think it's a knife, so I'm going to test it's a knife based on the thing that's most different to a spoon.
Yeah, okay. I mean, mentally, it feels like if I do, it feels like if I'm touching something, it's ambiguous, then I say, oh, it could be X, and then I test X. And if it's not, I say, oh, well, it could be Y, and then I test Y, as opposed to, I don't feel like I'm testing them all at the same time or jumping around rapidly. I explore one hypothesis, then I get and try the next hypothesis, and try the next hypothesis until I get the right one. Which I think is consistent with what you're saying here.
Yeah, I think so.
Yeah,
and this is just showing.
You use the second most likely one to inform how to test the first one.
Right.
So you like.
Yeah, I mean, it's interesting. The second most likely. I don't know how do you determine the second most likely? What was it? I missed that, but
it's just based on the evidence scores.
Yeah. Oh, I see. Based on your evidence scores. I mean, if I have a whole set of cutlery, all have the same handle, then they're all equally like. I guess maybe I use forks more than I use knives. I guess I don't know.
But yeah, they might all be pretty likely, so you might compare it to any of them, but you're already very certain it's not your cat or like some object that's totally different.
I'm just saying there may not always be an obvious second most likely. There may be a set of things that are equally likely at some point in time. Like all the cutlery has the same handle, and I may be 4 different types. So I just, there's no one that's more likely than the other, and I just would have to pick one.
Right.
But I guess the system wouldn't have a problem with that. Would just say, well, okay, they're equally likely, pick one.
Yeah.
Yeah.
That would just be kind of random noise which one it picked. Yeah, and this is just showing that this also works with the distant agent. So here the distant agent, because it's this kind of ball and socket eye-like agent, it kind of moves around at a point, but then it can jump in space to then look down at a different part of the object, which is what you're seeing here. And then after that point, it jumps over here to can then look down at the handle. And whenever it arrives at a particular location, then it starts doing its kind of random-like walk over that area. This is again the distant agent where it first tries to test this side of the object, the spoon, and then it tests the other side. And then you can kind of plot what are some of the hotspots for testing based on this policy. And as you'd imagine, it's kind of extreme edges of the objects like rims and handles. And again, with the things like the fork, it's the 2 ends of the object. So that was kind of more qualitative results. So I can just show a few quantitative results. These are kind of, this policy was implemented a while ago, but just showing that kind of when we implemented this, what was the effect on the system. And so all these results are when we learn and test on all 77 objects in YCB and where we have noise in the data. So this is showing, for example, the amount of location noise that there is. And it's worth just mentioning maybe so kind of what you were asking about earlier, Jeff, like clarifying the kind of correct or like when the model is correct about its most like its kind of final output versus when it just gets the most likely hypothesis. So if you imagine that the true object is the mug in scenario 1, the mug has the most evidence, so it's correct in its most likely hypothesis. But it's only in scenario 2 where you have this significant difference in evidence that enables the system to converge. And so in particular, what this is
you're saying in scenario 1, it wouldn't converge in scenario 1?
Well, it hasn't converged yet.
Oh, okay, but it would, wouldn't it, eventually? I mean,
potentially, yeah, it should eventually, but it might not always. But the reason I'm mentioning this is because when we report the results of Monty, sometimes we just look at whether the most likely hypothesis was correct, and sometimes we look whether it actually converged to the correct hypothesis.
It should always, it should always converge eventually, but when we run experiments, we set like a maximum amount of steps just because we want to keep the runtimes at a reasonable time. And then that way, sometimes it just times out and we say, all right, you had enough time, you didn't have enough certainty to make a classification. But
and I guess even with lots of time, if there was like noise in the data, like if it just couldn't disambiguate them, it might never fully converge.
I think often just going with the most likely is often good. I mean, imagine I have a cabinet full of coffee cups, and one of them has a chip on it, on the a little defect on the side, right? And so I know that one is a separate item object, just say, for example. I don't know, maybe there's something else different about it. But I reach into the cabinet and 9 out of my 10 coffee cups are the same. I pick one up and I just assume it's one of the 9, and then and that's good enough. And then maybe later my finger brushes across the broken part and goes, oh no, this is the broken one. My point is I don't have to search through all my hypotheses all the time. I at some point you just say this is good enough and I'm going for it until I accidentally discover like, oh no, there is a difference.
Right. Yeah, and that's kind of the strength of this evidence-based approach, that we can act at any point in time and just use the most likely hypothesis. Like we don't need to 100% recognize the object yet. We can just act on our current hypothesis. But right now in this kind of research stage, we wanted to really get to scenario 2 as quick as possible, which is why we want to have these efficient policies that quickly get to a high confidence on which object it is. So that's
so scenario 2 would be, in your example, like trying to move to the location where your chip on your coffee cup is and actually see if it's there.
Right. I mean, it's interesting because there's a scale here. Obviously, I don't want to confuse the coffee cup for the fork. That's not going to work, right? But confusing the coffee cup for another one that's very similar to it, or a fork for one that has maybe a slightly bent tine. I don't want to spend all my time, in life looking at all the minutia, right? It's like, okay, let's keep going until we discover otherwise. And then when something happens that's unexpected, I go, oh shit, something happened. So I guess I'm saying there is a spectrum of when scenario 1 is acceptable and when scenario 2
Right.
is.
Yeah,
Yeah,
and
this isn't meant to
example-
be a criticism of scenario 1. It's basically just a preamble because I'm going to show some results from its accuracy in this setting when this is sufficient,
Right.
and its accuracy in this setting, like when we require it to be this confident.
Well, it's also like when people do benchmarks on object recognition or something like that, they might say, well, did you determine this particular version of this object or something like that? And maybe that's not what we want to do all the time, only, it's in a practical system, you wouldn't always need to go all the way to scenario 2. Obviously, in the objects you're showing here, you would, but in the case of a fork or the bent tine or one that's a little bit different, you wouldn't necessarily have to. Okay, thank you.
Yeah, no worries. So yeah, with the distant agent, so it used to be before we had this policy, the distant agent was essentially confined to its starting location and looking around in that space. So we saw quite a significant improvement in accuracy there. So I mean, in this
This is doing what?
This is
Top up.
recognizing all 77 objects with noise.
I'm trying. What are the two scenarios there? With
sorry. So
top
red
down
is
policy.
Yeah, red is the kind of baseline where it just kind of moves around randomly. The blue is where it also can jump to the desired locations.
All right. Okay.
But here, there's a smaller. On the next slide, I'll show a bigger difference. Here is where we're not required to converge. So that's this scenario on the left. So
Yeah.
we just need to have the correct most likely hypothesis. And you see there's a reasonable improvement, but there's not a huge one because in this case, often our hypothesis was correct. We just were never able to look on the other side of the object to confirm it. But in this case, we have to, it's the second scenario, this one, we have to converge for it to be considered correct. And here there's a much bigger improvement because it's very hard for the distant agent to converge when it's confined to, one side of an object. Often the disambiguating feature is just not present. And so there was, like 45% increase in accuracy.
Yeah, and I mean, with these model-based policies, the main measure that we want to improve there is the number of steps. So quicker convergence. Ideally, we would have good accuracy in both cases. I think this is more of an artifact of the distant agent only getting one side of the object, like only one view of the object if it can't jump, and then it can't disambiguate some objects from each other.
Right. Yeah.
Yeah, and on that note, it does significantly speed up inference for the distant agent. And so this is just showing the number of steps to convergence, where each point is an episode and the cross is the mean. And then for the surface agent, it was a smaller improvement because if you imagine like the surface agent was already able to fully explore the kind of surface. And so when it wasn't required to converge, it's only a 4.5% improvement, where you do need convergence, 14%.
Okay, well, because the surface agent can move around the object over
Exactly, yeah.
And the distant agent can't.
But I think it's worth pointing out, like 14% is still a pretty significant improvement. If you consider like a typical benchmark, and particularly, the closer you get to 100%, the more you start kind of having ceiling effects where
well, I think the biggest you're already at 80% with the baseline. So right.
But and similarly, I think there's kind of ceiling effects with the so there's only a bit of an improvement with the speed for the surface agent. And I think partly what this is there are just some objects in YCB that are kind of very difficult to disambiguate. Potentially they're only different based on color. And the surface agent, if it doesn't have access to color, then it's never going to converge, even if it can jump to kind of different points. But it just gives a bit of flavor of the kind of quantitative effects of having that policy.
You know, it's interesting to think about in the YCB data set. Let's
Yeah.
say you have two objects that are only different by color. If the surface agent is like a finger, then there aren't two objects. It's just one object. I mean, it's like they don't know,
and
don't know the difference.
that's something that like we recognize, but yeah, is currently not kind of reflected in how we measure accuracy on YCB.
Right.
But it would be really nice to have that. Yeah.
It reminds me of when I talked about auditory objects, like the sound something makes, right? And you know, like the sound the cup makes when you put it on the desk. Well, there's lots of objects that can make that same sound. So it's not like, oh, the auditory column would say, oh, that's a coffee cup, or that's a phone, or that's a plate. It would say, oh, that's a sound of a certain type of sound I recognize of ceramic hitting the countertop. And yet, so it doesn't know about those other classes. It doesn't know anything about coffee cups. I just know the sound. I recognize the sound, and then we can associate through voting that sound with a particular object. Like, oh, that could be this object. That so it's similar to that in the sense that a touch object which doesn't have color wouldn't know different objects only differ by color. It's not like it says, oh, I can't tell the difference between these. It's just they're the same. And through voting, you know, the visual object, the visual system would have to distinguish between the two. I just think it's interesting to think about when we do these, as you said, as we do these tests, to bear in mind that it's not always appropriate for the system to differentiate objects that are undifferentiable in the particular modality we're dealing with. And that's not a failure of the system at all.
Right.
Right.
Yeah. Yeah. And speaking of failures, so there's just some, I think, interesting cases. It's not necessarily a core failure, but just kind of quirks and how it works at the moment. So, for example, we don't currently use kind of absence of a sensation, so like negative information. We haven't yet implemented how to, or like a way to update the evidence for objects based on that. It is in our pipeline to do that, but what that means is like, if we're currently on this part of the handle and we go to this point in empty space because we think the spoon or the knife are oriented that way, and we don't see anything there, the system just moves back to where it was before, and it doesn't use that information in any way. But actually that information tells you a ton about the orientation of the object or the potential ID of the object. The fact that you were expecting there to be something there and there wasn't.
So do you view this as just something we haven't done yet, or something we don't know?
Yeah, exactly. It's just we haven't implemented it yet. But we definitely think it's important. Instead
of getting a failure case A, we might call it, you know, work to be done.
Right.
I mean, it's the word failure seems pretty, you know, like, hey, it's broken.
Fair enough.
Yeah, it's not a failure. It doesn't recognize the sound of an object because we don't have an auditory sensor, right?
Yeah, and then I've kind of alluded to how eventually you want to do this more in like feature space, and when you're kind of calculating the distance rather than just like Euclidean distance between points. And so what that means is like in some instances, like it might say like, oh, this handle is more different than this handle. Like it focuses on this part of the object rather than the head of the fork versus the head of the spoon, because physically these are more separated, even though clearly these are the more kind of interesting parts that are going to tell you something different. And then something I just noticed in terms of the efficiency of the policies is often the same locations are visited, and so that can just be a bit inefficient. And I think you can imagine kind of some model-based ways in which you might avoid kind of revisiting the same locations again and again.
It's interesting just think about personal. When I touch something, I often do exactly that. I touch the same things over and over and over again. It's like a fidgeting, you know, if I'm holding a pen in my hand, and I'll often just move my finger over the exact same parts of the pen over and over and over again, like, you know, play with the clip or something like that. This is just an observation. I'm not sure why the brain is doing that, but But I often do that. But it seems like my cortex is sitting there just like testing the same thing over and over and over again. I don't know why,
Right.
but it does. It's not like I'm thinking about it too much, but like I'll be thinking about something else, but I'll be fidgeting with the pen and just repeatedly touching it the same way or twirling it the same way or something like that.
You're
So
starved for
brains-
stimulation.
I don't know if I'm starved for stimulation, maybe, but it feels, yeah, maybe the cortex doesn't want to do nothing. It's like, I want to do something. Okay, I'll just keep doing this over and over again. But it's not like I'm really actively well, I'm not consciously testing something. I'm not consciously sitting there going, is this still the pen? Is this still the pen? I'm not conscious of it. Maybe that's what the columns are doing. I don't know. But it's interesting that just I don't know if it's meaningful. I just make that observation that we.
How else would you learn behavior and changes, right? Like if
Well, you
win-
do it, yeah. But once I know it, why would I do it over and over and over again, right? Like something I do is like some pens have like a little clip that you can it's like springy, right? And if I have one of those pens, I will often stick my finger under the edge and just push it up and down a little bit, and I'll just do that, constantly.
It's clear, the need for that is clear in adversarial situations. When you have an opponent working against you, you always want to verify that things are the way you think they are, because through actions not of your own, they will change in surprising ways.
Right, but that makes sense, but does it really make sense in the case of the pen? I mean, I've been holding this pen for 20 minutes. I've held it every day. I mean, I don't know.
You're the one who says it's the same mechanism for all the things. So maybe it's just that degenerate case of that mechanism.
Maybe, right. Degenerate case, this mechanism sitting there going, well, I got nothing else to do, so let's keep testing this.
I mean, you basically look at it, there's a subtle reward involved in it. And then, in an extreme case, you would have OCD, right? Where you keep repeating the same actions altogether.
Kevin. Right. But, there's some pleasure in it, right?
Yeah.
There's some pleasure in verifying that this is the pen that I know.
Or just the tactile sensation is a reward in itself.
Well, I don't know about it. Feels to me
you don't have to be goal oriented for everything.
Well, it does feel like when I do this fidgeting, I'm actually it's not just, and I do the same thing over and over and over again. It's not like I'm just moving my finger all over the place. It's like I do the same behavior over and over and over again.
There is like a certain pattern, I think, to fidgeting in terms of like, it's often kind of mechanical things like, or like,
right.
I don't know if it has some relationship to, reward associated with like, I don't know, tool making or something like that. Like, snapping a stick or something like that. Like it feels more similar to that than like any possible random thing, which is like just touching a flat surface or something like that.
Right. There is something salient about it. I'm fidgeting with the salient component. Like we don't want to spend too much time on this. If I just sit and talk to someone and I'm sitting across the table from them and talk to them, we know that the eyes are continually saccading between the eyes and the nose and the mouth and the ears, and just 3 times a second. It's for 10 minutes. As long as you're looking at them, that's what you're doing, and that's it. Basically, again, sort of just looking at each. I don't know. They're looking at the same features over and over again. Maybe they're changing. I mean, I don't think it's worth a lot of time on this. It's interesting to point out that somehow there is I think Kevin's right. There's some sort of reward for verifying this hypothesis, and you just keep doing it, and it could become OCD at some point.
Well, some people have these kind of tics when they're trying to concentrate on something, and it can either be, sometimes they listen to certain music and the rhythmic patterns in the background, or some repetitive motions, are kind of like it triggers something in the process of concentration that somehow is reassuring or reestablishes something.
We're getting pretty far afield here, right? I agree with you. I just want to point out that I just observed this, like, hey, I do move my finger all the time over the same things.
Right.
but I agree with you. We don't want to change this in terms of what you're talking about here. We don't want to do that.
So yeah, and I guess just in terms of people who are actually using the policy, just to be aware that at the moment it's implemented in a way that the agent kind of teleports to the location it wants to go to, and so you can imagine the kind of analogy for this is like we essentially have the kind of higher level policy goal state of like being at a particular location in the environment that gets passed down to say more subcortical structures, which would kind of actually initiate the movement through space, simple walking or whatever that's necessary to get there. But to avoid kind of having to implement that and coordinate that with the kind of realities of the environment, at the moment, we just kind of move there instantaneously.
I think that's right. I mean, the cortex, basically, if you think of the output of the cortex, I always imagine it's the inputs of the cortex are sort of movement vectors, like you go in this direction for at this speed for this amount of time. The output would probably be something similar. And so the output say, okay, I want to get to some location. I should move in this direction, it's some speed and time. But it's actually not doing it. It's just sending that signal to somebody else who's going to try to do it. So in the eyes, it sends a signal to the colliculus, which actually knows how to do those things. Right. So I think, in fact, if we're it's basically saying, go here and let someone else take care of it. There's nothing embarrassing about that at all. That's what we should be doing. So.
Yeah, I think that will tie into like the second part, the go states, and kind of you talk about that later, like how output go states, and then like the subcortical areas can take care of executing and getting to those states.
Yeah, and then I guess just the final point on the local graph mismatch that's being used is just how kind of when we bring in hierarchy, you can imagine this being a lot more efficient. So it's still the same idea. You have kind of learned models aligned by their most likely poses, but then you do kind of distance and feature space to kind of determine where to test. This is not currently implemented, but actually we could add this quite easily once we have our scene level data set fully implemented, with using Rami's SDRs.
One other alternative that ties into like maybe like making it more like it would be easier to imagine how the brain would do it, and it might be more efficient, is just kind of storing these hotspots that you showed earlier in the model of the object. So for example, for a face, we would just store that eyes, nose, mouth are kind of hotspots to go. And you could either calculate the hotspot, like calculate these a couple of times from the graph mismatch, or you could kind of infer them whenever you make a movement, and it gives you a lot of evidence, or like kind of makes you recognize an object. Then you add that as like a high salient point in the model.
Right. And then, like Jeff was kind of, no, definitely. Yeah. And like Jeff was alluding to earlier, then you can like kind of, then you're just testing an object. You don't really have to like this definitely feels like the more deliberate thing of like, okay, you're given a really hard task of like, I don't know, you're at a dinner party and there's a game where you have to test what's in a cardboard box. And so you're really thinking about the possibilities. But in most day-to-day life, like you say, you're probably using a more simple heuristic of just like, oh yeah, I tend to feel here, and then that tells me what it is.
Yeah, that's a good way of putting it. Like this requires some cognitive resources to figure out where do I go best to distinguish these two objects, and you need the whole model of the objects to calculate that. Whereas just having like some hotspots in the object model that are good points to go to recognize that object would be like a much more efficient way just to kind of have a general policy for each object.
Maybe.
Kind of like a
yeah, thanks for bringing that up again, though. I think it's a while since we talked about
that. Kind of like having minimal distinguishable features. A set of those.
Maybe.
Yeah.
I think. I think one thing we have to bear in mind, if you go back to the picture of the that one there, like you say, oh, okay, so the whole feature, we're gonna look for this feature, the knife end as a feature, right? That's the idea here, the hierarchy.
Yeah, exactly. So in this example, like we've talked about how with hierarchy you could use fewer points to kind of represent objects. And so already this is going to be much more efficient because we're not comparing thousands of points, thousands of other points.
I think the thing to bear in mind on this is what we discovered about hierarchical compositional structure to begin with, is that the key to solving that problem was to say that a feature doesn't have a location. Like the hammerhead doesn't have a location, right? It has many locations which are all part of the hammerhead or all part of that feature, and we do it on a location by location basis. I don't, this is in the paper we're writing. So there isn't a location for the hammerhead. It's like you could go to any point of the hammerhead.
Right.
As long as you know which point of the hammerhead, you can say it's supposed to be a hammerhead here, and I happen to be at this location right now, or I mean at that location now, but you'd still test it. I just want to remind everyone, we don't want to get in the habit of thinking like, oh, a feature has a location in space. It doesn't. It has many locations in space. And I mean, like a composite object built up of other objects. So objects have no specific location. They're located on a point-by-point basis relative to other objects.
No, that's a good point. I made this overly
I'm
simplified.
not saying you didn't do that wrong. I'm just pointing out that when we think about
No, but I think it's a
problems,
good point in terms of how we
Yeah.
represent it, because we don't want, as you say, like a single point and it's like, oh, that's where the hammerhead is.
right, this is the big lesson.
But
Just
we can
want
still, I
like that.
guess, use fewer points. Like we don't need
Oh
to
yeah,
then
right. Oh yeah,
cover
in
the
fact,
thing.
Right. I mean, it's almost like if I was moving from, let's say I was moving from the handle of the to up to the end to see if it's a fork or a spoon. It doesn't matter actually exactly where I land on the fork or the spoon part. It's as long as I know as long as I know the location and I know what I'm expecting to see, I don't have to go to the same location. It's just any location on the spoon part or any location on the fork part will work because of what? It's a
Right.
subtle thing. Not everyone understands it. It's a subtle thing that's really important. We'll just have to keep that in mind all the time.
Right.
So,
Yeah, and then just on the distance and feature space. So I am assuming here that, for example, we're representing object kind of features like coming in from the lower level in the hierarchy with something like SDRs where there's some overlap based on the similarity of the objects that have been learned, similar to the work that Rami was doing where, you saw this clustering, and then so you can imagine that, in SDR space, this mug is very far away from this spoon. But with hierarchy, maybe you'd have this kind of concept that the two handles are nearby in SDR space, but the two heads are distant.
yeah, I feel like I still feel uncomfortable with the SDR overlaps.
Right.
Maybe it's like Einstein being uncomfortable with quantum mechanics. So he just couldn't accept it, and he just spent the rest of his life trying to prove it wasn't right. And maybe I'm like that. I'm just gotten too old. I can't get it. But I still want to raise it. I still feel uncomfortable with this. I don't have an alternate solution. So I have to think about it.
No, that's right. I mean, but I'll try not to, I guess.
Well, we're going forward with it, so you're baking it into the system. So,
Yeah, but I guess we're baking a lot of things into the system while they work. But it can.
Well, this
change.
It's a pretty fundamental idea whether it's going to do this or not, and the fundamental idea is like, what is the nature of representation, and that's pretty basic. So anyway, go. I'm not going to stop you. It works. If it works, it works. I'll just be a curmudgeon.
In terms of multiple objects, I'll just briefly touch on this. That we have kind of this move back on object policy, and this uses information. So when you have multiple objects in the environment, basically the learning module just tries to stay on the object it believes it's on until it recognizes it. And this uses information about our kind of most likely hypotheses as well as where the learning module is on the object. So it's also model-based in that sense. And so, our multi-object setting currently looks like this, where you have kind of a target object like this pink Lego block, and then you have some other objects kind of placed around it in space, and then you're saccading over the objects, but you may move on to other ones. And the kind of basic principle is like as you're moving over the actual object. So in this case, the potted meat can is the one you're starting on. The evidence for that object is building over time. But if you suddenly go on to another object, in general, you're going to get a bunch of observations that aren't consistent. So evidence is here on the left. And so that's the steep decline in evidence you're seeing here. And this is reflected. So on the x-axis, these lines are indicating what the ground truth of what the sensor is actually looking at. So here it's looking at the potted meat can, but here it starts looking at other objects. And so the kind of learning module can internally detect that change in evidence and kind of, retrospect that, okay, something's very different now. I'm now sensing something very different from what I was confident I was on before, and then initiate an action to move back to where it was.
Well, what should the
kind
goal
of around
be?
here.
Is the goal to say I need to keep going back to the meat can, or should the goal be saying, oh, okay, I'm onto a second object and I'm building a composition or
Yeah, so
structure?
we can also do that with hierarchy, but here the assumption is we want to like, because then yeah, exactly. Then you just say, okay, I was on a pod meat can, but now I'm on something else, and then in the higher level learning module, it's going to now be representing that, okay, at that previous location there was a pot of meat can. Now we're looking at something different.
Right.
But
As soon as you
there
start
will
getting
be at least some instances where we want to kind of figure out what we're looking at before we start looking at other things.
right, and if it's
Yeah,
in the
I
learning
mean-
module, you can't learn hierarchy, right? There's no concept of like, oh, where is
Right.
this object relative to the other object?
Yeah, so
Sorry.
there are kind of two objectives. This one just shows this plot shows detecting when we left the object that we were previously on. Then we have two
Mhm.
choices. Either we reset the evidence and we start detecting a new object, or we invoke this policy that Niels mentioned and
Yeah,
move back onto the object that we were previously on and continue recognizing that object.
Mm.
And it's a bit fast maybe, but this is showing that in action where we start on the golf ball, do a few saccades, and then get on the mustard bottle, and then kind of immediately move back because we realize that's something different. And this gives us about a 10% accuracy improvement when we move back on the object in this setting of kind of distractor objects that are on either side. Cool. So then that gets me to model-based policy in abstract spaces. So in general, when I was kind of thinking about this again, it's very speculative, but it feels like there's the kind of the point Jeff was making before. There's tons of instances of model-based abstract tasks, but in general, when I was thinking about them, they don't really, they're not really directly analogous to classification, but there's definitely similar principles to this idea of kind of like mentally rotating and aligning different representations and kind of what you call it, focusing on the differences and the similarities, but particularly on the differences. So, you can imagine, for example, you have some taxonomy structure for how to classify species. One might be based on DNA analysis, another might be based on fossil records. And so there's two different taxonomies. And if you kind of align these in representational space, there'll be parts of this tree-like structure which may be the exact same. It doesn't matter which system you use, it's going to kind of classify the species in the same way. Or there might be kind of regions in this structure that are very different. And it's, if you know one of these systems well and you're learning the other one, this is the system you want to focus on to understand it. Or similarly, imagine you're reading a paper, let's say on a machine learning technique, and it's a kind of sparsity paper. So the introductions are going to be similar, and to kind of jump to the early figure that shows their kind of main technique in a kind of abstract form. And of course, these don't have a direct analogy in physical space. It's more of a kind of slightly abstract space of kind of the structure of the paper. But then when you're kind of scrutinizing the actual algorithm, you're operating in more this kind of mathematical space where, again, you're looking at the kind of similarities, aligning those, kind of almost superimposing them on one another, and then scrutinizing the key differences between them. That was everything I had on the abstract space, unless anyone else wanted to talk about that. But then I was just going to briefly talk about hierarchy. So yeah. So for all the policies,
now we're switching to
relatively
hierarchy.
simple.
That picture says we're going to hierarchy in terms of interacting with the world as opposed to inference and
yes, yeah, bringing in hierarchy for policies.
To a goal-oriented behavior.
Yeah, and generally for most interesting things where we want to change the state of the world, we probably need some degree of hierarchy.
Right, I mean, but we were just talking earlier about hierarchy in terms of inference, you know, so
Yeah.
it plays roles there too. But we're really
Right.
talking now we're going to talk about hierarchy in terms of goal-oriented behavior.
Right.
I'm assuming, given the picture.
Yeah, exactly. Yeah, again, this is much more speculative. I mean, this is stuff we've had brainstorming sessions about and talked about, but it's not something we have kind of any super concrete proposals for. You can imagine, you know, for example, you want to make coffee, how this kind of process can be broken down into these kind of hierarchical spaces, day planning, the kitchen space, coffee machine space. And within each one of those, you might have a particular action you need to do that can be kind of further decomposed. And so far, kind of the approach we're thinking or that's kind of evolved is to have kind of goal states that learning module can send. You can either send that to a low-level motor system, which would initiate a model-free policy, and that's essentially sending stuff to subcortical structures to kind of take care of simple tasks, or it can send it to another learning module, which is more of a hierarchical model-based policy. And that way, with the latter, you can kind of break down complex actions into goal states that can further be decomposed into by low-level object models. And so going back to the cortical anatomy, I mentioned the direct motor projections, but and those go from L5, but L5 also receives top-down feedback via the apical dendrites in L1. And there's kind of connectivity between L5 and L6. So maybe there's some circuit in there that can support kind of a higher level cortical column saying, okay, you need to initiate this particular type of, or you need to kind of enact this particular kind of goal state. And then where appropriate, a lower level learning module can then kind of output its requirements to the subcortical structure, which, as you were saying, Jeff, is like the only actual output in the cortex, and so the only way it can actually change the state of the world.
This is you know, it's a fascinating area. Well, I should let you finish maybe because
yeah,
I'm assuming we don't really understand this very well. So,
no,
but maybe you do.
no,
but you know,
yeah.
it's funny because you know the classic motor output goes up the hierarchy in the red lines here, which at first made no sense to me. You think just like in the coffee making example, you want to decompose actions going down the hierarchy, but the purple line there really is in some sense. I mean that is your feedback, and so that has to be if we're decomposing things going down the hierarchy, it's got to be the purple line there, and so you know maybe it's like layer 6 we're talking about, it's like a location. So maybe you know region 3 says this is the location I want to be at. And somehow the column below it says, okay, that's where you want to be. I'll help you get that up. And then it says, oh, I want to be there. And again, in the way we're talking about it in the paper we're working on, these 3 columns are co-aligned. So they're all sort of looking at the same location in space, but that's not always the case, right? So it's very confusing. I just want to point out that these are some of the parameters we have to deal with, but it's very confusing. But I feel we can solve this problem. I think there's a really clean answer to it. Maybe you've got something else to present.
No, not really. Yeah, the only thing I was going to say, in terms of like
sorry, just on this picture, I guess, like it shouldn't, like it might give the idea that we want to have a direct motor connection back to layer 5, where basically the higher level column tells the lower level column exactly how to act, but actually it just tells the lower level column the state it wants to be in, and then the lower level column uses its models to figure out how to get to that state. So we might not need that pink direct connection. It might be going through like layer 4 and layer 6 and whatever models we learned there to figure out.
So that's correct. I mean, think about it. If you watch the purple line, the major connection from the purple line is up in layer 1. And so it's basically saying to a whole bunch of other columns below it, you know what, this is the state we want to be in. This is in some sense like this is you all want to be in this location, or I don't know what the state is yet, but you want to be in some state. The little synapses in layer 6A are more for the columns that are actually co-aligned. But you're right. We're trying the upper region is not telling the lower region what to do. It's saying this is the state we want to be in. And it says, okay, I'll try to implement that state for me. And then it tells the guy below, okay, that's the state I'm trying to be in. It tells the guy below, region 1, like, okay, that's what I'm trying to be. But it's still really confusing because all these have a motor output. One of the questions I've always had, is we label these 2 red lines as motor output, but is there are they equivalent, or is it more like one is somehow hierarchically higher than the other motor output? Do they both go to the same motor system, or do they go to some hierarchical representation subcortically of the motor system? Like if they were both going to the superior colliculus, would one be sort of implementing a higher level superior colliculus function, the other is a lower level superior colliculus function? I don't know.
Yeah, because like you could imagine how this might be the kind of scene level representation of the kitchen, and you're trying to make coffee, and so it sends the goal state of having the coffee machine on to a learning module that knows about coffee machines. So maybe this direct motor output is more like moving through space, as in like walking. I don't know. And then so this one will get you towards the coffee machine. This will more direct your arm to actually turn it on.
I think I think there's a whole bunch of things in flow here.
But yeah, there's obviously a lot of complications.
This is like one of the things that bothered me for decades. Like, how do we understand decomposition of motor behaviors, given that the cortex is a sensory motor system and that it's output? And I felt like I never really had enough information to go on to answer this question. But now I feel like we do, with the idea now that this idea that we come up with is that the hierarchical composition is a point-by-point compositional structure, and it's not an object-to-object compositional structure. In some sense it is, in some sense it isn't. But anyway, with the new insight about columns and being able to represent the same space, a location in 2 different columns hierarchically arranged, I feel like all of a sudden this is the clue that is going to help us unravel this problem. So all I'm saying is I feel confident that we now have enough information to really come up with a very solid compositional, hierarchical, goal-directed or model-directed theory of motor behavior. And we have a long way to go to get there, but I don't think it's going to take that long. I mean, we have a lot of things to solve, but I don't think it's going to take that long. I think we have the information we need now.
Right. Yeah, and in terms of like non-aligned receptive field, like we were talking about earlier, a natural idea is that with this kind of decomposition of hierarchical policies or hierarchical goal states, you would kind of recruit the motor cortex where necessary for more complex motor actions, where these are essentially just learning modules that are specialized in coordinating the movement of a body part. But yeah, what those anatomical connections look like and how exactly you coordinate that, it's all obviously of complexity there.
Yeah. Anyway, it's something we can work on, and maybe it's something we can solve when we get together in January. How about that?
Yeah, I feel like this would be a perfect subject for the brainstorming week.
Great topic to think about beforehand and really try to spend a few days just really working on it. I mean, we made progress on the whole hierarchical composition. Vivian and I worked on that. We made progress on that a while back, and maybe we can do the same thing here.
Yeah, and so just kind of bringing this together. So this is this overview diagram many of you will have seen, where you have the kind of outside world of the mug on a table, hand and eye. Those are sending to the sensory modules. You have these motor modules, and then learning modules that are modeling the objects. And in red are the kind of motor projections of some kind. And so the kind of model-free policies generally exist kind of in this domain where it's just this direct sensory motor loop. Not involving to any kind of significant degree the cortical areas, the learning modules. And it's worth kind of noting that the input to a sensor module and an output from a motor module is not compliant with the cortical messaging protocol. But all these other solid lines going throughout the system are, including the projected goal states. And then, a model-based policy is more when you have a learning module involved with kind of coming up with a action that it's going to send to this kind of more subcortical motor system. And then a hierarchical model-based policy is more when these learning modules are kind of interacting together with these top-down connections. And then
I
should be last slide.
I'm
Oh, yeah.
gonna get a call, and I'm gonna get a call in 3 minutes, and when I do, I'll have to drop off, so keep going.
Okay, yeah, this is the last slide, but just to say that, yeah, in terms of future work, so I think the quick thing to do that we've been wanting to do for a long time is just better model-free kind of policies for the distant agents, so just saccadence salient features and the kind of medium feature, so it's grayed out, is kind of more exploration-focused policies. We focused a lot on inference, and those, again, wouldn't be too difficult to implement. And then the more complex thing, which is why it's grayed out, is the hierarchical policies for the multi-step goals. So things like setting the dinner table and all that kind of stuff.
Making coffee.
Yeah.
Yeah.
But yeah, as you said, that might be a good topic for the upcoming, by the way.
Well, you can solve it before then, great, but it's like my experience is you have to think about these things for a long time, and then they sort of gel before at some point. Yeah. Yeah. That was a good summary of everything.
Yeah. Thanks, Niels. That's great.
Right.
Cool. Yeah, no worries.
We have a sensory motor system. We have to figure out the motor part. So this is where we are. Excellent.
I know we
yeah.
got to be departing and stuff, but if there's just one question I could ask, has to do with hypotheses and estimating pose. So as I understand it, the current hypothesis system is about just object identity. So like, let's say I've figured out that I'm on a cup.
Right. Yeah. So it does also test for pose. I kind of tried to show that, but maybe I didn't make that.
We have that in the code today. Did we build that?
Yeah.
Okay.
So I bet I can show you a specific slide. So that was this one. So disambiguating the pose. So in this instance, we know it's spoon.
Mm-hmm.
But it doesn't know the orientation of the spoon, so it first tries so it has two basically.
But in this case, to say it was a spoon, it already had to have the orientation was either it could be off 180 degrees. Like it's the question, the more general question is, what if the spoon was rotated 90 degrees? How did you recognize it, or how did you come up with a hypothesis?
We don't know for certain yet that it is a spoon, but we are. Like it's a lot more likely than the other objects. Like you could imagine we've already sensed the top of the spoon, and that kind of curved area is not consistent with any other object that we have, maybe.
I guess what it's not clear to me is how did you decide on the particular orientation? When you start out, you have no idea what the orientation is.
Yeah, but so here it's like felt the handle. I mean, I don't know, I don't remember exactly how I got this figure. This might not be the most realistic one. But because, if it's only felt the handle, how does it know it's a spoon? But yeah, to Vivian's point, let's just say it's most likely how it's a spoon. But anyways,
how did it even get to that testing orientation, right?
Well, because it's felt the handle, so it knows that the handle is oriented like that. But the handle could be reflected on that point, and so
right. But what if the handle
these are essentially
that? Is like how do you?
But that wouldn't be like the spoon couldn't be oriented like this because it's felt all along here. And so it knows the handle has that orientation.
I guess the question
that orientation is consistent with this orientation.
When you start moving, you have one point of observation. Then you don't know the orientation.
Yeah, but we're not already. This isn't after one point. This is after multiple points.
Right. But sensation. Where along the way you were deciding the orientation and the potential object? You had to be testing different orientations, I guess, is the question.
Yeah. So. I mean, like at the moment, it already starts with like many hypotheses for the possible orientations. If that's what you mean, like, yeah, it starts with. It's a fairly
I think that was the question.
In that sense, like it starts with an exhaustive.
How does it do that? I'm not asking you. I think that was the question that came.
Yeah, sorry. Was this
can you make a hypothesis-driven jump? Like, let's say we already know we're on a spoon, for example. Can you make a hypothesis-driven jump just to resolve the pose?
Yes. No, it's a great question, and the answer is yes. So that's what it's trying to do here. So in this case, it's doing a hypothesis-driven jump to this red location to try and tell if the spoon's oriented like that or if it's like this.
Okay.
And then here, it's trying to disambiguate like a more subtle difference in the pose. Like, is the spoon like this or is it like this? And so it's jumping here.
Okay.
But no, it's a good question.